Good afternoon. Welcome at the Faculty of Aerospace Engineering. My name is Maurice Hoogreef. I'm the session chair here this afternoon. And it's my pleasure to introduce to you the next speakers, Group 27 on the Everwing.
Okay, good afternoon everyone, and thank you for coming to our presentation on the Everwing, a fully zero emissions, recyclable, 150 passenger commercial aircraft. Before we start, let's go over the agenda for today. I will begin by explaining what exactly our aircraft is, what inspired its design, and why we believe it is so crucial to the future of aviation. After this, we will go into some more details about the design of our aircraft, before finally going into some depth on the sustainability goals that drove our design. So, let's first start with the why. In 2026, climate change has become undeniable. Rivers are drying up, glaciers are melting, and the Earth as a whole is becoming less inhabitable for living things, including humanity. In fact, everyone in this room, I'm sure, has felt this today. The heat wave that we are going through is no coincidence. It is a result of continued negligence of humanity to treat climate change with the respect and urgency that it deserves. Something has to change, and commercial aviation is one of the biggest contributors to this problem. Per passenger kilometer, commercial flights create more CO2 than any other modern mode of transport, and 20% greater than the next most polluting method. In 2025 and 2026, this has been okay. However, leading up to 2050, if nothing is done to prevent it, this could become a much larger problem. Why, you may ask? Well, that is because by 2050, worldwide aviation is expected to double. More passengers, more flights, and more emissions. In addition to this, the ICAO, International Civil Aviation Organization, plans to reduce emissions of aviation operations to net zero by 2050. The titans of the industry, Boeing and Airbus, have done little to prevent this, and as sustainability and emissions requirements become more stringent, they will inevitably fall behind. And this is where we come in. The Everwing has focused on the narrow-body market for commercial aircraft. There are two main reasons for this. The first is that the narrow-body market is by far the largest of all commercial aviation. From all of Airbus's wide-body programs throughout history, they have combined to a total of approximately 3,800 orders, while the A320 family alone has combined to a total of almost 20,000. The second major reason is that short-haul flights and domestic flights create substantially more emissions than long-haul flights do, and narrow-body airliners fly short. In this market, we see a future in which we can go from a fossil fuel-dependent aviation industry to one in which flight is renewable, sustainable, and zero emissions. We see a future in which aircraft no longer follow a linear life cycle, but are rather used for the next generation. And we see a future in which aircraft go from being left in boneyards to being built 100% recyclable. In order to achieve this desired future, we have extrapolated three main goals driving the design of the Everwing. The first is net zero in service emissions. The second is full end-of-life recyclability. And the third is minimized environmental impact over its lifetime. We have done this all while providing superior performance to the A320 and Boeing 737. Let's look at some stats. This is the life cycle CO2 equivalent emissions of the A320neo projected to 2050. And this is the Everwing, almost 10 times lower. In terms of recyclability, this is the A350, one of the newest aircraft on the market. It is composed of 53% CFRP composites, which is a wholly unrecyclable material. If recycled, it loses up to 30% of its structural performance and releases large amounts of fine particle emissions. This is the Everwing. It is composed completely of fully recyclable materials, with each allowing at least 80% of recoverable mass. This allows the Everwing to break the traditional cycle of cradle to grave and make its way back from grave to cradle. In addition to these three main goals, there were a couple of other driving design requirements for our aircraft. The first of which is a cruise speed of Mach 0.8. Of course, passengers would like to reach their destination in a similar time to if they flew in an A320. The second is a capacity of 150 passengers, which is on par with its competitors. And finally, our aircraft also had an 80,000 kilogram maximum takeoff weight limit with a 4,000 kilometer range. Next, let's look at some of the major design choices made for the Everwing. The first is flying fully off of liquid hydrogen fuel cell propulsion. There are a couple of major benefits to this. The first being extremely high gravimetric energy density. Per kilogram, it produces more than 3 times more energy than standard aviation kerosene. In addition to this, it is zero emissions, producing zero CO2 and NOx emissions throughout operations. This is vital to ensuring that the Everwing stays net zero. And finally, it is extremely renewable. After all, hydrogen is the most abundant resource in the universe. The other main thing that we designed our aircraft around is the blended wing body planform. This allows for superior aerodynamic performance to a conventional planform, minimizing drag and leading to our second major benefit. This major benefit is fuel efficiency. Using a blended wing body planform, we have up to 30% reduced fuel consumption, which not only lets us save on volumetric and weight space in our aircraft, but also allows us to source less fuel over its lifetime, which reduces its footprint. And finally, the blended wing body offers a large amount of volumetric space. This is crucial for flying on liquid hydrogen, as while its gravimetric energy density is very high, its volumetric energy density is lower than that of standard kerosene. With a blended wing body, we are able to store as much hydrogen as we need without worrying about space constraints. Next, to talk about some of the more detailed design concepts is my colleague Bart.
Okay, thank you very much, Ethan. Following the past 10 weeks, we have designed an aircraft. It looks as follows, the Everwing. If we look a bit into the details of the aircraft, some main takeaways are the body itself. It has a large body which produces part of the aircraft's lift, where for normal commercial aircraft, most of the lift generated by the fuselage can be neglected. Also, we use tails for stability and 4 engines powered by hydrogen fuel cells. If we zoom in a bit more on the cabin itself, we have to accommodate for 150 passengers. This has been done by generating a seating arrangement of 3-4-4-3, with only the first row being a bit different, where we have 1, 4, 4 and 1. Here, some big differences can be seen with respect to commercial aircraft, where, for example, the A320 only has a 3-3 configuration. Our cabin is much wider, but it's a bit smaller in length. To store hydrogen that we use to power the fuel cells, we need to have circular pressure vessels. There's not a lot of space to store it, for example, in the wing, and therefore we store these tanks in the fuselage of the aircraft. 2 tanks will be located next to the passengers, where they are separated by a wall, and one of the tanks will be in the back of the aircraft. This all results in a total fuselage length of 21.4 meters and a width at the widest point of 12.2. If we look a bit closer into the cross-section of the aircraft, it can be seen that the fuel tanks are shown here in green. The aisles where passengers can walk are shown in blue, and the seating areas are shown in red. To be able to fly at our cruise altitude that has been set to be 40,000 feet, we need to pressurize the cabin to create a nice environment for the passengers. This has been done by creating a 3-bubble structure, where we have one bubble over here, which goes around the fuselage, one bubble in the middle, and again on the same side another bubble, where there will be added a structure, a skin in the middle to have not too much wetted area where the bubbles are located. Also are there some blue struts, which can be seen over here, which help reinforce the bubble structure. In terms of propulsion of our aircraft, we use hydrogen fuel cell powered engines. The fuel cells will be stored in the core of the engine itself, where hydrogen, gaseous hydrogen will power the fuel cells, and with that generated electricity, a fan in the engine will be spun. Heat generated by the fuel cells will be moved away from the engine by the heat exchangers, which are located in the flow of the engine itself. If we look a bit more into the performance of the engine, it can be seen that the engine can achieve a thrust of around maximum 15 kilonewtons and a maximum power of 4.6 megawatts per engine. This is quite a high number, but with current technologic developments, it can be assumed that these technologies will reach technology readiness level 9 near the years of 2050. These engines, we will locate them on the back of the aircraft, where 2 engines will fit between the tails, and the other engines will be outside of the fuselage, connected by struts. The hydrogen needs to be moved from the tanks to the engine. This is done by hydrogen fuel lines, which are shown in blue. Also, some hydrogen needs to be moved away. This is called venting. This is done by the orange lines. For example, for a boil of hydrogen, we can vent that away via the orange system. This hydrogen is led to the tips of the wing, such that the hydrogen vented away does not get in close contact with the engines and therefore not opposes any safety risks. Since the fuselage also provides some lift to the aircraft, we need smaller wings. The way we size these wings is by looking what should the total surface area of the aircraft be. From this, we subtracted the fuselage area, and therefore we came up with the areas that we need to have for the wing. Performing general sizing methodologies, we came up with the following wing design, where one wing has a span of 11.14 meters. Since we want to fly at a cruise speed of max 0.8, this wing has been sized with a supercritical airfoil. Therefore, when we fly at these higher cruise speeds, we don't get any Mach waves forming on the wings, and therefore we don't get any increased drag. If we add these wings to the fuselage, we see that the final span of the aircraft becomes 35.5 meters. Therefore, as can be seen in the green, we nicely stay within ICAO airport reference code C, which also fits the A320 and the Boeing 737, and therefore we stay compatible with these kind of aircraft. The longitudinal position of the wing has been determined by looking at the longitudinal stability of the entire aircraft. This determined the location that the wing needed to be from the nose of the aircraft. Only then we needed to space the wing vertically. In the middle, by the red block, there is an emergency exit. Therefore, it was not possible to fit the wing in the middle of the fuselage. Putting the wing below the emergency exit would cause structural members to fall outside of the fuselage and would make it harder to structurally integrate the wing. Therefore, the wing has been moved up above the emergency exit, and therefore the wing nicely fits within the airplane structure and can easily be integrated. For its stability, the aircraft uses two V-tails, where the tail is inclinated with a dihedral angle of 70 degrees. The tail has a rudder vader to provide yaw and pitch control. During takeoff, this pitch control is sadly not enough, therefore extra elevators have been added to the wings of the aircraft, and roll will be performed by ailerons near the tips of the wings. If we look from the side to the aircraft, the tail has been fitted on the back. In orange, there's an extra structural member added, which makes sure that we can keep the wing in an upright position and make sure that the rudder does not get into the boundary layer created by the fuselage. Well, now we know about the design itself. What does this mean for the total aircraft mass? The operating empty weight of the aircraft is 41.5 tons. It's able to store 60 tons worth of payload, only needing 3.8 tons of hydrogen to fly to its cruise destination. This altogether results in a maximum takeoff weight of the aircraft of 61 tons. In terms of costs, the aircraft to develop the entire system, the entire aircraft, is 9.76 billion euros. To produce one aircraft on its own is 64.5 million, and the market price of the aircraft will therefore be 105 million euros. This results in a return on investment of total of 40.3%. Now that we know a bit more on how the aircraft looks, I would like to invite Rowan to talk a bit more about the recyclability of our aircraft and its life cycle.
Thank you, Bart. I will now take you through the remanufacturability of the aircraft and its life cycle emissions, starting with the material life cycle. The aircraft is mainly made out of three materials: CFR PEEK, which is a carbon fiber reinforced thermoplast, aluminium lithium alloys, and in some small amounts titanium. So for manufacturing of the aircraft, steps are quite straightforward. You do the material sourcing. After that, the parts are manufactured and assembled into all sub-assemblies. All these sub-assemblies are combined into the final assembly, which is the fully operational aircraft. After its full operational life, we have to disassemble it. So you return it to the final assembly line, disassemble all sub-assemblies, disassemble all parts, which can either be refurbished and put back into the part manufacturing, or can be recycled, after which the recyclate will be put back into the material stream. So let's look at two examples. For this, we have the wing spar, which is made out of aluminium lithium alloys, and the skin panel, which is made out of CFR PEEK. So for the wing spar at the manufacturing, again, steps are quite straightforward. You source the aluminium, you manufacture the spar, you assemble the wing system, and then you enter operation with a fully functional wing. After its lifetime, it returns from operation, disassembles the wing system, extract the spar, and then you inspect it for damages. After inspecting it for damages, you have two options. One, you refurbish the component, and it's a new component which can be used on a new aircraft, or you melt the component down, and then you have new materials which can be put into the material stream. For the skin panel, this looks roughly the same. You start with the material sourcing, you manufacture the panel, you assemble it into the fuselage, and you enter it into operation. After operation, it's a little bit different. You return it from operation, you disassemble it, and then the main difference happens is you extract the PEEK matrix, which is the plastic that holds the carbon fibers together. You inspect these carbon fibers for damages, and after this, you can refurbish the fibers, and they can be used as a new material in the material stream. Next up is the life cycle assessment. For this, we assess the climate change potential of our aircraft throughout all of its life phases. So from raw material extraction to the manufacturing and assembly, also throughout operations, including with the liquid hydrogen sourcing, the maintenance and repair, and in the end, the end-of-life recycling. So let's first look at the raw material extraction. As introduced before, our aircraft is mainly made out of CFR PEEK and aluminium lithium alloys. Together, we are looking at a rough CCP of 951 tons CO2 equivalent. Next up is the manufacturing and assembly. For this, we took the A320neo as a baseline, scaled it with our operating empty ratio, and took into account the 2050 EU grid emissions improvements. Together, this gave us a manufacturing CCP. So for operations and liquid hydrogen sourcing, we have said our operations are fully net zero, so our main CCP is coming from the green hydrogen sourcing. For this, we took a 1-to-1 emission factor, where 1 kilogram of CO2 equivalent emissions are introduced into the atmosphere for 1 kilogram of hydrogen. Together with the utilization rate of the aircraft, this gives us a liquid hydrogen sourcing CCP. For the maintenance and repair, the main driver are the fuel stacks in the fuel cells for the hydrogen engines. We calculated that for our lifetime of 30 years, we need roughly 2 replacements of these, and together with the shaft power of the engine, this gave us a maintenance CCP. Lastly, end of life, which was the goal of this entire project. Main driving factor of this is the material recovery efficiency. For CFR PEEK and titanium lithium alloys, or titanium alloys, this is about 80%, and for aluminium lithium alloys, this is about 90%. Take that together with the avoided emissions through the remanufacturing process, the energy required for the processing and disassembling, you get a negative net burden throughout this end-of-life phase. So all of these CCPs have been calculated and put into this graph for you. As you can see, the main CCP emissions thing is the liquid hydrogen sourcing. This is also quite sensitive to the way we source the hydrogen, either using green energy or still fossil fuels. Zooming in, we can see the raw material sourcing is the next worst driving factor behind our climate change potential. And I would like to highlight our net zero operations and our positive impact throughout end of life. With that being said, let's look at our goal. Our mission was to design an aircraft for 150 passengers that is fully recyclable and achieves net zero operational impact. With the Everwing, we have shown that this is possible through the use of recyclable materials and sustainable propulsion technologies. The Everwing is not just a concept. It represents a realistic vision of what future of aviation can look like. And by designing it today, we have taken one step closer to making that future a reality. Thank you so much for joining us.
Thank you very much, Team 27. I would like to invite the rest of the group forward as well. And it means we have about 20 minutes for questions.
Yes, as one of the engineers from Airbus, thank you very much for your presentation. Well done. Of course, one comment, we do care about sustainability, and one of our first priority of Airbus, you see it on the website, we develop a sustainable future, and this is extremely difficult, as you might have seen in your project. So that's why I also get directly to a few questions actually. Hydrogen. You are doing cryogene hydrogen, and you store that next to the passengers. What about your crashworthiness and fire safety?
All right, so you're asking about the fact that we use cryogenic hydrogen and store it next to the passengers. What does that have to, how does that relate?
Let me put it that way. At the moment you have a crash and you do not ensure that the fire will break out, your passengers are basically surrounded by fire of more than 1,000 degrees that you don't see.
But just to clarify, we are repeating the questions for the live stream.
Yeah, oh good.
Yes. All right, well, if my colleague Martin would like to answer.
Yeah, thank you very much for the question. I think it is probably the largest concern with dealing with hydrogen, and specifically with liquid hydrogen, is the storage and the crashworthiness. Whilst yes, I think it poses quite an innate, I guess, sense of maybe fear having the passengers close to a liquid hydrogen tank. But we see a failure of the tank in itself a catastrophic failure. That if the tank were to fail and liquid hydrogen or hydrogen itself would escape into the cabin, that is seen as a catastrophic failure that would be unsurvivable for the passengers. So by taking steps before that and with internal crash structures between the inner and outer walls of the tank, or external crash structures such that the tank itself can break through and absorb the energy of a crash, that the tanks will be able to survive a crash that is survivable, and that way we could mitigate the risks that are caused by having the tanks close to the passenger.
That's a challenge. Just two other questions. So, what about the CG shift if you burn down the fuel?
All right, so you're asking about the CG shift burning down the fuel.
Yeah.
Well, I think Floris would like to answer.
Yes, what about the CG shift during burning of the fuel? We've considered this, of course, for longitudinal stability. And as for the longitudinal wing placement, we've placed it such that it's always after the neutral point, meaning that for any loading configuration, so whether it's fuel burned, whether there's payload in there, it should be inherently stable. As a matter of fact, I have an additional slide to illustrate it well. If you could.
Yeah.
Yeah.
I don't see the details. Fantastic.
Yes. So this here is basically what answers your question, as far as I know. Well, what you see on the x-axis is the wing position, so x leading edge, mean aerodynamic chord. On the y-axis is the CM alpha slope. And basically what you want is you want to pick the point where both the orange line as well as the blue line, so the most forward and the most off CG cases, you want those to be located where the CM alpha slope is always negative, and that's the. For any, well, as you can see, if we have a lot of payload, then the aircraft becomes inherently more stable since the payload is located very far forward for the aircraft.
Okay. Good. Thank you. Then my last question, then I'll stop. Okay, then because I'm over. You know why balloons are round, right? So if you make a double or triple bubble, we had the issue with the AG8. It's an oval. It's not a circular fuselage. It's an oval, and it gives a lot of difficulties in your structure. If you look at the maintenance program of the 747, where do you have all the cracks? Exactly at the interface between the upper bubble and the main fuselage. How do you want to cope with that?
So how we want to deal with stress concentrations from a non-circular fuselage? I think my colleague Ron
Yes.
would be happy to answer.
For the triple bubble fuselage structure, we have considered mainly the amount of bubbles and then the structure behind it. The airframes that are there are also there to support the outside of the bubble, and then the struts are there to make sure that they don't expand too much. Into maintenance, we have not looked that deep in it, but we are aware that this is where the biggest stress concentrations are within the triple bubble fuselage.
Regarding maintenance, I'm willing to say a
Yeah,
little
you
bit
were-
extra about that. So obviously because the double bubble design is not inherently new, the maintenance thereof, yes, it is more complicated. That is very true. But these procedures exist, and maintenance, repair, and overhaul organizations, MROs, are trained in these kinds of things. And therefore, our maintenance relies mostly on the novelty of the design. For example, the fuel cell stack introduces some extra maintenance difficulties, especially since these are troubles that aren't known with MROs, and therefore a lot of operational efforts do need to be introduced for this project to become feasible. And therefore we would like to see this project not only as a design we do, but as a communal effort of the entire aviation sector, so to speak.
Yes.
You made a very deliberate choice for fuel cell architecture and fans. Why did you not go for combustion of hydrogen? where the TRL is probably higher, the hydrogen engine combustion, where you could probably save a few billions on your development cost and be faster on the market, flying greener more quickly.
All right. Well, I believe colleague Benza.
Sorry? Oh, so yes, the question was why we didn't go for hydrogen combustion instead of the hydrogen fuel cells. And the main reason is due to the high burning temperatures of hydrogen and the nitrogen. As much as possible. So now we only have water vapor coming out of the engine, basically. So that was the design drive behind using fuel cells, PEM fuel cells instead of hydrogen combustion.
Additional question: if you would go for, if you have the down mark of having NOx emissions, how much faster would you be on the market with maybe a combustion engine rather than a fuel cell engine? Can you estimate that?
We did not estimate that. Our project was about 2050 entry, and we did research into what is going to be available then. And also another big part of the project was low impact. And we determined that this made lower impact than what a hydrogen combustion engine could have achieved. Thank you.
Yeah, my colleagues already asked all my questions. I'm from Freightliner, so congratulations first with your design. I'm very interested in the engine, but what is the range for aircraft? Do you think with this fuel cell hydrogen engine you will be able to cover that?
So your question was
150 passengers.
correct. So with 150 passengers, can we cover the range with fuel cells?
Yes, thank you. Yes, we can. We run analysis, and then we model the engines, and we model the fuel flow. And based on the fuel flow, we sized the tanks. For our 4,000 kilometer range, plus getting up to altitude, plus getting up to speed, we calculated around that we would need to use 3,080 kilograms of fuel. Our tanks are sized for 3,800 kilograms of fuel. So hopefully we would have plenty to go to our range with loiter and emergency maneuvers and everything else.
Do you think the infrastructure will be ready by 2050 for that?
So the question was if the structure is going. If the infrastructure is going to be ready by then. Well, in the project itself, we assumed that it is already going to be ready. However, I can give the microphone to Ethan, who knows more about this.
Thank you. By infrastructure, do you mean refueling infrastructure at airports? Well, yes. As of now, of course, there are no hydrogen planes flying commercially. However, we've done some research into developments of hydrogen refueling sources in airports. For example, even just in the Netherlands, Rotterdam Airport, as can be seen with Delft, is doing a lot and testing out liquid hydrogen refueling. In addition to this, Schiphol and also Groningen Airport are testing out hydrogen refueling for ground service vehicles, and this could, we believe, by 2050 be changed quite easily into an infrastructure for hydrogen fueling for aircraft.
Can I add to that question?
Yes.
Being responsible for the daily operations at Rotterdam Airport, I have some reflections on indeed what you're saying. And part of the infrastructure itself, I'm also wondering if you have considered anything on what your airplane would have in terms of other requirements for airports. How would my operation, so to say, be changed by your aircraft?
All right, so in terms of, the question was about operations in airports, are there any other things that might be changed by our aircraft? Well, in our design, we attempted to minimize the possible changes that airports would need to make to their infrastructure in order to make it as easy to enter into the market as possible. Early on in the design stages, based off the ICAO aerodrome reference codes, we believed we would be landing one code higher than we ended up, which would have made us not able to fit into all gates. However, all A320 type gates. However, we shrunk it down, and for our final design, we believe that one of the only differences will be the refueling infrastructure.
Okay, thank you.
Right?
So, because the hydrogen aircraft is already a big leap, why did you choose to challenge also the materials paradigm and the recyclability in the same time?
So,
complex.
Question then, you mean that why did we choose to do both hydrogen for net zero emissions and full recyclability at end of life in one aircraft? The reason for this is we believe that in order to sort of spark truly meaningful change in the industry and make it clear to the world that it is possible to have a much more sustainable future, that to design an aircraft that does both, we believe would be the best option to do that. In addition to this, in terms of recyclability of aircraft, aircraft are already rather quite recyclable. It's not as much as our aircraft, but we believe that it would not be it would be feasible for us to attempt to also design for full recyclability.
I have another question. How many doors do you have?
I believe my colleague Jelle can answer. So how many doors are on the aircraft?
Yeah, so yeah, just for the live stream, how many doors does our aircraft have? And yeah, I think that might also be a question which comes from the safety concern. And indeed, I can definitely understand that. We, as a team, looked into how passengers can actually be evacuated from this aircraft in a similar time, so the 90 seconds that is used in general aviation right now. Yeah, what was implemented in our design, which makes us different standard one aisle tube and wing aircraft, is for us that we have 3 aisles. This is something that the blended wing body design choice accommodates for, and that also means that our cabin is not as long as other cabins from the A320 and the 737. So, for example, that means that whenever you're seated halfway, this would be equivalent to being in roughly row 7 of maybe an A320, and then the direct distance to your exits, either at the front or at the back of the fuselage, would be the same to the distance at the wing of the A320 and, for example, the front of the fuselage. And furthermore, in finding out what door types were needed, we had a look at the CS25 regulations, and with the Type C and Type 2 doors that we implemented in our design, we are totally compliant with the safety regulations there.
So you have roughly 2 times the number of passengers as in an AC-20, and when we developed the AC-21 ACF, we had to put a 3rd door in behind the wing because we did not comply with the rules for evacuation. Just to give you.
We have 150 passengers.
150?
Yes.
Ah, I understand the number wrong. Okay, then it fits. Okay.
We have time for one more question.
Maybe then I have a question on this material that you're using, this teak material. I'm not too familiar with that. Some people might be, but how common practice is it already to really reuse it?
So the question was about our material CFR Peak and about its recyclability. Well, CFR Peak is currently being researched. It is not yet TRL 9. It is a sort of it is a carbon fiber reinforced composite, but it uses ether ketone as a matrix, and it is much more recyclable than standard CFRP because of the fact that the matrix is a thermoplastic rather than a thermoset. This allows you to, through for example, burning off the matrix, save the fibers without losing a lot of the structural integrity that might have been lost if you were using a standard. In addition to this, there are a couple of methods, such as glass fiber delamination, that are being researched, in which you can keep both the matrix and the fibers without losing much of its strength. Another method, for example, is solvolysis, in which the matrix is broken down and is able to be reformed with the fibers taken out.
You assumed 80% recyclability. Is that already what is in the lab, or is that?
Currently, 80% estimate that we have taken based on a couple of different papers that we have looked at. Some of the other methods that I discussed, and glass fiber delamination, can have up to 95% mass retention. However, for the sake of future changes, as it is not yet TRL 9, conservative estimate.
Yeah. Okay. Thanks.
Right. Thank you very much for your questions and your answers. I think it deserves one more round of applause. Then for, I think, 8 of you, today also ends your bachelor studies here. And to celebrate that, we have and make it official diplomas. So I'd like to ask the tutoring team. Is your coaches are they here?
I'm coach.
Yeah,
Coach and the other coach, I don't know.
Okay.
He is right now. So
If you would like to hand out the diploma, then maybe
yes,
say a couple words.
I will say a couple of words. What is in the nice folder? Great. Yes. Okay. Well, good afternoon, everyone. My name is Julia van Kamp, and I'm the one who dreamed up this weird assignment where I wanted them to build a fully recyclable aircraft. I think they succeeded quite well, but now we're here for actually something which is a bit more joyful even than the whole DSE. It was beautiful to see you work on this project, but now, well, as already was mentioned, 8 of you are also getting a diploma, and I have the honor to give you your diploma. So what I'm going to do is I'm first going to hand them out one by one to the 8 of you who already get it today, and then I would like to take a group picture with all of us and the diplomas, if that's all right. So, great. We will just go in alphabetical order, and the first diploma I have here is for Bart. So, Bart, congratulations. And very important, otherwise we also have this highly engineered well, safety container for your diploma.
Thank you.
Please be careful of it. Next diploma I have here is for Floris. It's a politician's handshake, you need to. And also for you, the container. There you go. Then, Berit. There you go.
Perfect, thank you.
Then, Ethan. Well, thank you, and there you go. And next up is Bense. Congratulations as well. And well deserved. So there you go. Next one is Martijn. En natuurlijk also folder for you. And the final, no, not the final one, Jelle. There you go. And Jose. And now I need to look, I think, yeah, here there's one more. I was already missing one. So now I think while we line up to take a group picture, because it would be nice to have a picture with all of you, and also the others who do not have a diploma right now will have one very shortly, so it's more of an administrative thing. So please line up here a bit. What is very nice as well to mention for this group, I don't know how that came to be, but well, actually I think 7 of you are going to do flight performance and propulsion after summer, so the Masters in Flight Performance and Propulsion. Well,
sir, can I make a suggestion?
Yes.
Everybody move.
We will move for the picture. Yes, that's a lot better. Thank you very much for directing it. By the way, I also did not introduce my colleague Olaf Snoosma, who was so kind to supervise this group together with also our other coach, Nick Papalamos, but he's not here. So, well, everyone say Everwing, I guess. Yeah. And now like we have fun. Congratulations, well deserved. Yeah. Congratulations. Congrats. Ja, klein beetje gefeliciteerd. Hij komt, ja, het is net iets minder.